Okay, let's go ahead and get started. Exam one, there was a one mistake. The right answer was marked incorrectly. I corrected that on Friday, or actually Thursday. Then there were a few questions, and I need to go through and make sure that everybody gets credit for it. The correct answer was ortho-para directing, mainly because the steric effects weren't that huge. And you got to remember, you got a static, you got a statistical 2-to-1 ratio. But I will give credit for para. In that case, both of those answers will be correct. I'm going to go through and make sure that everybody has credit for those. I still need to verify that. Okay. So there were 3 questions, I believe, that had ortho-para as the right answer. I'll accept para. Okay. Because there is an argument for the steric effects. Okay. If you only put ortho, there's not a reasonable answer for ortho. Okay. All right. Any other questions about exam one? Okay. All right. What I tell everybody on the first exam is if you don't like your grade, what you should think about is how you prepared for that exam and what you can change. Go through your exam and identify everything you missed wrong and look at it as far as learning outcomes. So was it a Diels-Alder type reaction? Was it a directing effect? Was it a nomenclature question? And then once you've done that, you can see that you might have missed a specific area, right? If that's the case, right, you just need to be more thorough on the next exam. You might have also, what's common is you might have also just not gotten all the details. So maybe you got most of the Diels-Alder, but you didn't get that regioselectivity, right? So that regioselectivity for that Diels-Alder question, you just need to be a little bit deeper in how exact you are on it. If you study the same way for exam 2 as you studied for exam 1, you should expect the same result. So you can modify what you're doing to improve your grades on that. Okay. I wasn't surprised by the grades. They were pretty decent overall. The only question that was obviously answered incorrectly, I fixed that. That was my mistake. But the rest of them look pretty good. And like I said, I'll give you credit for the 3 ortho-para and para questions, and I'll verify those grades hopefully by the end of the week. Okay. All right. Where we are is we're going to finish up chapter 18 today and then chapter 19. So we got a couple more topics in chapter 18. So we looked at multiple substitutions on last Tuesday. Those weren't on exam 2. So 3 substitutions. So you may see electrophilic aromatic substitutions on the next exam. Okay, but with the other 2 topics we have is the nucleophilic aromatic substitutions and then the elimination addition reactions. Okay, nucleophilic aromatic substitutions is opposite of what we were doing with the electrophilic aromatic substitutions. If we look at this reaction, there's a few things that has to be in place. So if I take this group here, I can substitute that halide for this hydroxide. Okay, this is not a general reaction. There has to be several things in place. The first thing is I need a strong deactivating group. Right? And the one that you're going to see most often is the nitro group. Right. You could have an ammonium salt, but as you can see, we're using a base. So it'd have to be a quaternary ammonium salt with all methyls on the nitrogen. The second thing you need is you need a good leaving group. And for this, you're going to see mostly halides, right? That's about the only one that works well is halide. So that would be chloride, bromide, iodide. And then you need the right orientation between your deactivating group So your strong deactivating group, right, needs to be nitro, good leaving group. And then the arrangement between your leaving group and your deactivating group, your strong deactivating group, needs to be either ortho or para. Meta won't work. The way this works is that the hydroxide acts as a nucleophile. And like with the electrophilic aromatic substitutions, it's important here to go ahead and show all the resonance structures. So here you can see that we get a negative on the ring. So that's going to push that there, right? Which means this has to come out to there. Then we get this group, right? And then when that can go one more. So we can get this group, and then next reaction. Okay, so we delocalize. So if we think about it, although the nitro group is a deactivating group in electrophilic aromatic substitutions, in this case, what is it doing? It's stabilizing that negative charge. So in a nucleophilic aromatic substitution, the nitro group acts as a activator or a stabilizing group. And I'm going to redraw this over here to go to the next step. So this is just a redraw. So if you don't want to redraw it, don't worry about it. What happens is this comes down, this goes around, right? And then here we lose our best leaving group, which is the bromide. And that's how we get to our product. Questions about this one? So this one's very specific, right? It has to have certain characteristics for this to occur. So nucleophilic aromatic substitution is very restrictive. The nucleophilic aromatic substitution also does the substitution, right, at a very specific position, okay? So if we look at here, it's going to be this position that's being substituted. In electrophilic aromatic substitution, we had directing effects, okay? But in nucleophilic aromatic substitution, we are substituting wherever the halide is, okay? So there's no directing effects. We are physically substituting the leaving group. So synthetically, this can make a phenol, right, which is positive, but it can only make what kind of phenols? Nitrophenols, right? So there are a good number of nitrophenols but it is not a very largely used. Now, it does have a biological mechanistic counterpart. And so one of the reasons that you'll see nucleophilic aromatic substitution is there is a nucleophilic aromatic substitution that's enzyme driven in biological systems. The other reaction that we need to look at is electrophilic addition. I'm sorry, it's not electrophilic additions, it's elimination additions. Now, if you remember, we already looked at what if we just add sodium hydroxide, right, with some heat, we'll get no reaction. Right, because we're not going to get a normal SN2 style reaction. But if I increase the reactivity here, if I increase the reagents and I take this chloro group, and I really add a lot of heat to it, so not a little heat, we're going to add quite a bit amount of heat. And you'll see in a second why we need to do the second step. We can get this reaction to occur, but it doesn't occur through a nucleophilic aromatic substitution, and it doesn't occur through a SN1 or an SN2. What's happening in this reaction is we're actually getting an elimination. So we're adding a strong base with a lot of heat. And the first thing that happens is an elimination. So the base is going to pull this proton. These electrons go around to create a benzene. So not a benzene, but a benzene, right? Now we have a triple bond in that group. So this is the elimination portion. And then in the next step, base comes in, lose the electrons. We go back to just a benzene with a negative on that ring. This picks up a proton. Now, the reason that we have that acid as the last step is, remember, we've got a strong base here. This is a phenols are acidic. So the reason we add the H3O plus in the reaction is just to reprotonate this group. So we have an elimination followed by the addition, right? Then we're going to do a proton transfer. That gets us to this product here. Right? But then this product, right? We got to remember that we're in a strong base solution. So we pull off that proton. So then second step, we add acid to get us back to the phenol. Questions about that? Now, where this one is distinctly different, right, is the conditions. But also, if we look at this step right here, I showed the hydroxide coming to this position at the top, but could it have also come to that position? Yes, right? So it's going to go to one of the two sides of the benzene, the double bond, the triple bond. And so therefore there's two locations. When we look at the nucleophilic aromatic substitution, it always is going to attack wherever the halide is. Now we can also do this to make aniline. In this case, we use a strong base, sodium amide, in NH3, so an ammonia. Second step, again, we're going to need to acidify it afterwards. Okay, questions about this one? So in this case, I have a substituent, right? This is not a withdrawing group. This is a donating group. So we have the chloride, so we get elimination. That gives us the triple bond, but then the nitrogen can attack at two different positions. It can attack at the top, right? Or it could attack on the side. Yes, sir. Not, usually this has some heat, but the sodium amide is such a much stronger base that you don't have to heat it up to 300 degrees. So if we think about sodium hydroxide, it's a good base, but it's not a really strong base, right? It's got a peak, the water has a pKa of about 15.7, right? So if we look at ammonia, that's 35. So therefore, this would be a much stronger base. And since it's a stronger base, we don't need as much activation with the heat. And so you won't see heat here often. Sometimes you'll see 100 degrees, but you won't see something like 300 degrees. Yeah. All right. So the first one, nucleophilic aromatic substitution, is very specific, right? We've got to have that strong deactivating group or the strong electron withdrawing group, such as nitro group. We got to have a halide, and then we're only going to work in orthopara, and we always substitute exactly where the halide is. When we go down to electrophilic additions, right, there is no guidance on what type of group needs to be on the ring. It does need a good leaving group, such as a halide, right? But we also then have two possible positions that it could add, right? So we have two possible positions, not just the one. Okay. All right. That finishes the aromatic reactions. So let's move on into chapter 19. So aldehydes and ketones. So the aldehydes, right, we have a carbonyl with a hydrogen attached. So often generically shown this way. And then the ketone has the carbonyl and then two R groups, right? So between those two. We've seen aldehydes quite a bit, right? We've seen some ketones. We saw those in the alkyne reactions. So this is not a totally new functional group as far as reactions. And when we go through the reactions, we're going to go back and look at the review reactions first. For aldehydes, we're going to use the suffix al. And so for this one, we've got butanal, right? So if it is the highest oxidation state, we're going to name it as an aldehyde. And this one would be butanal. I don't have to number that because the al would always get priority as 1. If I had something like this would be 1, 2, 3, 4, 5. So this would be pentanal, right? The A here is telling me that this is all single bonded, so there's no double bonds. And then the Al is telling me I have an aldehyde. And then on the front of this one, I've got a methyl, right? So therefore I could get a 1, 2, 3 methyl. On ketones, right, we can name this as a butanone, right, where the double bond here, I have to put a number for it. So butanone. In a very complex one, I can drop the 2 into the back of the name, right? So right before the one. So for aldehydes, it's always assumed to be 1. Ketones, I got to put a number there. I also have a common naming system that we need to see about. You'll see it quite a bit, especially in biological systems. So this one here is also known as methyl and methyl ethyl ketone, and it is methyl ethyl ketone, although modern naming systems, we put the ethyl before the methyl, but this one is called MEK. MEK turns out to be industrial solvent. So we name this, we could have this one would be 3-pentanone, right? Or diethyl ketone. The other nomenclature effect is looking at, and let's start with an aldehyde here, but looking at this position, that position. We also have a identification on these that's a little bit different than the numbering system. Here, this is the alpha position. This is the beta, gamma. If you continued out, you get the delta and epsilon. And the alpha beta is going to be the one that we see the most in this class. We're going to be talking about alpha beta unsaturated. So if we added a double bond here, this would be an alpha beta unsaturated aldehyde. So let's try this. Give me the IUPAC name for these. Okay, so the first one, we get 1, 2, 3, 4, 5. So it's going to be a pentanal. The aldehyde has a higher oxidation state than the alcohol, so therefore it's going to get priority, right? Which then makes the alcohol 2-hydroxy. So 2-hydroxypentanal. If we look at the ketone, here we have 1, 2, 3, 4, 5. Seem to be stuck on 5 today. So pentanone, right? But I need to know where that double bond is. I mean, the carbonyl is. So that's 3. And then I have a substituent. And I'm going to give it the smallest possible number. So 2-methyl-3-pentanone. So if we look at preparation, first let's do review. That's where we'll stop today, is look at review of aldehydes and ketones. So preparation of aldehydes and ketones. And again, this is a review. We have an internal alkyne. We can end up with the ketone. Remember how this happened. All right, we get a proton transfer to the alkyne. And then we have the water then attacking that electrophilic position. And then at this point, right, we can get the tautomerization to occur. And if we look at this tautomerization, first thing we get is a proton transfer. Pulls that proton off, giving electrons back to the oxygen. And then the electrons come down. Giving us the ketone. So this process here is the tautomerization, right? And it can be either acid or base promoted. In this case, it's acid promoted because we're an acid. This group is known as an enol, right? So this would be the protonated enol. So we create an enol that then tautomerizes to a ketone. And again, this is from chapter 8, I think, the alkyne reaction chapter. When we're doing internal alkynes, we can use just acid and water. But when we have terminal alkynes, you usually see mercury salt as the catalyst. Now, this is still going to want to form the most stable carbocation species, which is going to be the secondary one. So on this terminal one, I'll still end up with a ketone. The only real difference here is you see that mercury salt, so that mercury sulfate. Some books will add the mercury sulfate to all of them. You really only need it for the terminal alkynes. Okay, so for internal alkynes, we get ketones. And terminal alkynes, we get ketones. How do we end up with aldehydes? How would we end up with a primary alcohol if this was an alkene? We'd use a borane, right? So we use BH3 followed by hydrogen peroxide and base. We're going to do a similar thing here, but we're going to use a slightly different reagent. So again, this is review, hydration, will use something like 9 BBN. What we want to use for the alkyde is some type of group where we only have one hydrogen. Okay, so it's still a borane. So you got BBN, 9 BBN. You could also have this one's not as common. Another one that you'll see is this one, sometimes shown physically, sometimes as a condensed form, right? But all of them have the same thing. They have one hydrogen on the boron. And what this will give us is 5 carbons, okay, is the primary aldehyde. So oxyboration, oxyboration oxidation. Questions about this one? Again, we end up with the primary enol, and then that tautomerizes to the product. In this case, it goes to the base process. Okay. All right, other reactions that you already know. Oxidation of alcohols. Okay, so if we use sodium dichromate, usually an acid, right, with a secondary alcohol, we'll end up with a ketone. But if we tried to do this with the primary alcohol, again with the strong acid, we end up with the carboxylic acid, right? So we don't end up with the aldehyde. So we end up with alcohol, and then here. So if we want to go from the primary alcohol to the aldehyde, instead of using the sodium dichromate or KMNO4 or one of the other strong acids, right? I'm going to use PCC and methylene chloride. PCC is the pyridinium salt. And the big reason that this will stop is actually the fact that the pyridinium chromochromate is organic soluble, right? And what stops this after the first addition is the fact there's no water, right? So we always want PCC in a anhydrous solvent. That's why we say methylene chloride. It's a common anhydrous solvent. Questions about these? So let's try some. So give me the reagents for these three. For the first one, right, we're going from an internal alkyne to a ketone. So there's two ways we could do this, right? We could just add, water and H2SO4. Or, right, or we could have done the oxyboration with the second step. We need the borane, right? That's the only one that'll work. We tried to use acid and water here, right? We'd end up with ketone. And then the last one, we're going from the secondary alcohol to the ketone. So here we just need an oxidant. So sodium dichromate and sulfuric acid. Yes, ma'am. No, they can't. So if we look at tertiary alcohols, we get no reaction. And that's because there's no alpha hydrogens. So if we think about secondary alcohols, right, it's this alpha hydrogen here that we're losing. And if we're looking at primary alcohols, again, it's these hydrogens. So for tertiary alcohols, we get no reaction with a strong oxidant or a PCC. Yes, ma'am. I just put HBr2. You could put 9BBN or one of the other. You just need one of the boron derivatives. Okay, questions? Yes, ma'am. No, because what would happen in the second one is if you used, so if we had used, is that the, yeah. So if we had used water, H2SO4 and mercury, right, that's going to give me the ketone. Because what you'll end up doing, right, is your first step is going to be adding the hydrogen to get the most stable carbocation. And then that means that the most stable carbide is going to be the second one. So when you add the water, it'll always be at the second position, which will result in a ketone. So I have to use an anti-Markovnikov style addition, which is the borane. Okay.